So now that we have the average interval velocity, we can actually try, and we can see that it's a linear pattern. We can actually come up with a linear function for the velocity. And if we use average the midpoint time, so for between 0 and 2 seconds, we'll use 1 second. So I'll just do it up here, 1 second. Between 2 and 4 seconds is 3 seconds, 5 seconds, 7 seconds, 9 seconds. We can see that there is a very simple relationship between the time and the velocity. So we can say that the velocity function, velocity as a function of time, is going to be just going to be t. Okay, so we know that at time 1 second, the velocity is going to be 1 meter per second. At 7 seconds, it's going to be 7 meters per second, etc. So there is our linear function that represents the velocity function. Okay, and we generated that from this displacement graph, and we did that by getting the slope segments and figuring out the slope interval, the average slope in those intervals, and using that average slope, we referred it to the average interval time, and we're able to come up with a function for that. Now that's not something that's very it's obvious at all, it's not evident at all, but there is this relationship that we're trying to exploit, this fact that we know that these quadratic type graphs end up with linear type changes or rates of change. Okay, in this case, our rate of change is going to be our velocity function. So we can try another one here. We have this, our time and our velocity, or our displacement, and we'll work out an average interval velocity here. So between 0 and 1 second, we increased by 3 meters, so we know that the velocity is going to be 3 meters per second. Between 1 and 2 seconds, we increased by 9 meters, so we know that that's now at 9 meters per second. Okay, it's going to be 15 meters per second. Okay, so here we increased from 32 to 53, so that looks like that's going to be 21 meters per second. Okay, and we went to 53 to 80 meters, so that's 27 meters in 1 second, so 27 meters per second. And again, we can use the average interval time, okay, or it's actually the mid-interval time, 0.5 seconds, 1.5 seconds, 2.5 seconds, 3.5 seconds, 4.5 seconds. And we can see if there's some pattern here. In fact, there is a linear function. We know this is a linear pattern. It's going up by 6s. Okay, so what we can do is we can work out our function here for velocity. So the velocity function, okay, so the function that represents velocity as a function of time is going to be 6, looks like if the time is 0.5, the velocity is 3 meters per second. So if we do 6 times t, okay, that should do it. So we can test that. 6 times 3.5 is 21. Yeah, 6 times 4.5 is 27. So there is our function that represents the velocity. Okay, so we started with our displacement function, and we were able to generate a velocity function from that, okay, or a rate of change function, and this happens to be a quadratic change. Okay, so we know it goes up by linear. The pattern, the first change is linear, and so we know the velocity ends up being a linear function. Okay, so what we're going to look at now is doing it now backwards. Now, how can we start with a velocity function and figure out how far they've gone? Okay, so that's now doing this a little bit backwards. So if we know the velocity, can we figure out the displacement? Well, if I know how fast I'm going, and I know how long I went, how much time I was going at that speed, I could work out my displacement by multiplying velocity times time. Okay. Now, here we have velocity. But the problem that we have here is, although I know the velocity at this time, and I know the velocity at this time, the velocities are different. So I cannot multiply just that velocity by this time interval to get the distance. So, okay, so what's happening here? So this is increasing velocity. So what's happening is they are accelerating. Okay, so the speed is constantly increasing. So we're not going on a constant velocity. Okay, the velocity is always changing and it's always increasing. So what would the position versus time graph look like? Okay, so the velocity, that's kind of hard to think of this now. So what's happening? The position is going to go slowly up. It's always going up. Okay, but then it's going up faster. So it's going to maybe look like this. Now, what we do know though is that if this velocity function is linear, then the position function is probably going to be quadratic. So that's why it's probably, yeah, that curved line will probably make sense. Okay, so let's take a look at these questions here. So it says, what's the slope of the velocity time, and what does the slope represent? So the slope of this velocity time, okay, let's work out a slope here. Let's zoom in. Let's do a slope triangle. You can do a different color to highlight it. There's slope triangle. Starts at 0 seconds and 3 meters per second. And let's just go to here. Okay, so we've gone from 3 meters per second to 15 meters per second. So we added 12 meters per second over 6 seconds. So the slope is going to be 2 meters per second divided by seconds, so 2 meters per second squared. Okay, so this is acceleration. Okay, the slope of the velocity time graph, slope equals 2 meters per second squared, and it is acceleration. Okay, so starting at time equals 0, distance equals 0, so we're going to start at that point. And what would the graph look like? Okay, so we're going from a slope function to a position function. So what would this graph look like? Okay, so let's kind of estimate. So let's say we're starting at 3 meters per second, and let's say, well, I've got a good idea here. Why don't we just do over this small time interval, okay, over the small time interval, we know that the average velocity is going to be, well, we started at 3 meters per second, and we ended at 7 meters per second. So why don't we say for the first 2 seconds we want an average of 5 meters per second. Okay, so for 2 seconds we went for 5 meters per second. So let's go, we would probably end up at 10 meters. Okay, for the first 2 seconds we're going to end up at 10 meters. And for the next 2 seconds, it looks like we ended up here at, looks like 11 meters per second. So we started at 7, we ended up at 11. So the average would be 9 meters per second for 2 seconds. So we're going to end up going 18 meters from here. So we're at 10. So we're going to end up at 28. So 28 would be right about here. Okay, so it's 28 meters per second. And then we can do the same thing for the next 2 seconds. So we can say, oh, well, the average velocity between, what's this going to be, 11 to 15. So it's going to be 14 meters per second. Is that right? 11 to 15. It's going to be 13 meters per second for 2 seconds. So we're going to go 26 meters. So that was 38. Okay, is that 38? We went from 10 to 28. and then we went 26, so it's going to be 54 meters. So there's 50, so let's say 54 is right about there. Okay, so we can see it's kind of curving up, and then we'll do the same thing for the next interval. We're going to have 15 to, looks like 19, so the average velocity will be 17, so we're going to, for 2 seconds, so we're going to go 34 meters now, so that's going to be 54 to plus 34 is going to be, looks like 88. So 88 is probably going to be somewhere around here. And we'll just do one more time interval. So from 19 to, it looks like it's going to be 23 meters per second. So the average velocity between 19 and 23 is going to be 21 meters per second. Times 2 is 42. So 88 meters here times 40 or plus 42 is going to be 130 meters. Okay, so we're going to end up at about, this is an estimate because we're just kind of, we don't know the exact velocity, but it makes sense to take an average. We're just averaging out the fastest and the slowest times in that interval, and we're going to plot it. And then when we do that, we can see that, yeah, this path that they're taking is a curved path. Since the velocity is linear, we kind of expect the position function to be quadratic, and that looks relatively quadratic. Okay, so there it is. We could do this many different ways, but this one seems to be pretty good. Okay, it seems to make a lot of sense. Now you could have done it a little bit differently. You might have taken the slowest time in each, or slowest velocity in each interval, but generally we still need a time interval and a velocity to work out distance. And so this is the way I did it. I took the average velocity in that time interval and use that velocity and time to work out the displacement over that time interval. Okay, now it wouldn't be wrong and wouldn't be as accurate, but you could have used the slowest velocity or the fastest velocity in that interval and done the same thing, and you would have just gotten an estimate of that position. But that's okay, that's what we're doing. We're estimating, just trying to figure out what this looks like. Yeah, and our analysis looks reasonable. Okay, and this is just analysis. We don't know how accurate this is yet, but we're just analyzing these things.